welcome to the deep dive.
Yeah.
Today, we're on a mission, really, to decode the secrets of large language models, LLMs. We're diving into two crucial questions. First, how do we truly know if an LM is actually, good?
Right.
And second, how are engineers and researchers making these incredibly powerful systems run faster, smarter, and just more efficiently in the real world?
Yeah.
We've got a stack of fascinating sources, and they should give you a real shortcut to being well-informed on LLM evaluation and optimization. And there are some surprising facts and practical insights you probably won't hear just anywhere.
It's such an essential conversation. I mean, LLMs show these incredible, almost magical capabilities, right?
Totally.
But actually evaluating their true performance and then making them practical, for real-world use, that presents some monumental challenges.
Yeah.
So we'll explore why just relying on a simple score really isn't enough, and how cutting-edge techniques are tackling these issues, everything from making sure the model's accurate to boosting its efficiency.
Kind of like peeking behind the curtain of AI's biggest stars.
Exactly. Think of it that way.
Okay, so let's peel back the layers here. Why is it so incredibly difficult, then, to tell if an LLM is actually good?
Yeah.
You said it's far from just getting a single benchmark score. What's the first major hurdle that always trips people up?
That's a great starting point because it really gets to the core of the challenge, the first hurdle. It's that every real-world AI problem just has its own unique quirks.
Okay.
Our sources really highlight this. Once you're serving production traffic, you'll inevitably find edge cases, specific scenarios you want to measure that a simple universal score just won't capture.
Right.
Imagine like you're building a recipe and nutrition system. It's not just about one final output. It's a chain of specific interconnected tasks. Is the system calling the web search API with the right query? Is it picking the best recipe? Did it accurately pull out the ingredients into structured JSON?
Okay.
If you only evaluate the very final step, you just won't know why a response failed. So more granular evaluations, they give you far more actionable insight.
That makes perfect sense.
Yeah.
It's like if your recipe system suggests you, deep fry a salad.
Right.
The problem isn't necessarily the final instruction, but maybe something much earlier in that chain.
Exactly.
So if we can't just rely on that single final answer, what about the metrics themselves? What are the sort of inherent quirks or flaws there?
Well, what's truly fascinating here are the, let's call them fundamental quirks of relying on just one metric.
Okay.
Take semantic similarity, for instance. It powers retrieval augmented generation RA by looking for similar phrases. So one study compared the phrase, "I like to eat potatoes," against 3 others. "I am a potato," "I am a human," and "I am hungry." They used 3 models, OpenAI's latest, and 2 high-ranking open source ones. And all 3 models, kind of surprisingly, chose "I am a potato" as the most semantically similar.
Wait, I am a potato. That seems wildly off.
It is.
As a human, I'd immediately go for I am hungry, or maybe I am human, as being more relevant contextually.
Right.
So the model is getting it right by its own metric, but it's completely wrong in terms of real-world meaning.
Exactly. It vividly illustrates how metrics don't always work the way you'd expect. And it reminds me of that baby cat videos versus a Carpathy lecture analogy from our sources.
Oh, yeah.
The cat videos got, 36 million views compared to the lecture's 4 million?
Right.
So if views were the only metric, you might conclude cats are better than LLMs, which is obviously absurd.
Yeah, the cat videos versus Carpathy lecture thing is a great reminder. Don't mistake popular metrics for true value. Views, even simul accuracy scores, can be completely misleading without that critical context, without a multifaceted evaluation strategy.
Spot on.
And that brings us to the common practice of using an LLM as a judge. That sounds really convenient, right? Just have one AI judge another. But what are the hidden pitfalls there?
That's precisely the challenge. I mean, using an LLM, especially something powerful like GPT-4, to evaluate responses is pretty common when manual review just isn't practical.
Sure.
But these models, they come with their own set of biases. A 2023 paper, for example, found GPT-4 aligns poorly with human judgment on short prompts.
Interesting.
It does better with longer ones, apparently. But LLMs can also, hallucinate details or rationale that sound plausible but are just plain wrong.
Right. The hallucination problem.
Or they inherit biases from their training data. Plus, they're limited by things like context windows and, of course, computational costs.
So we're dealing with these LLM biases. But it reminds me, you mentioned the McDonald's analogy in our sources too,
Yes.
where the instructions for cooking chicken nuggets were super specific,
Mm.
but mop the floor was just vague.
Exactly.
For performance reviews, you need specific feedback, right? Just like LLMs need clear, precise instructions if they're going to judge something effectively.
That's a perfect parallel.
But if even humans struggle with vague instructions, and we know humans can be biased, like that old SAT essay research you mentioned, where essay length correlated really well with score.
Yeah, nearly 20 years ago.
Right. So is truly objective evaluation even possible? Or is that asking too much?
That's a really deep and insightful question. And it gets to the core of what we're aiming for. Maybe true objective evaluation is, I don't know, an elusive ideal.
Perhaps.
But we can absolutely strive for reliably useful evaluation. And that brings us to the options available and how they kind of fit together.
Okay.
So you've got automated metrics, things like BLEU score, mainly for machine translation, and then a whole family of embedding-based similarity metrics, BERT score, cosine similarity, Jacquard similarity. They aim to capture deeper semantic meaning.
So these are like the quick, repeatable checks, good for initial development.
Exactly. Their big benefit is they are repeatable and they're great for those rapid development stages, like quickly testing different chunk sizes or overlap settings in our ROG system.
Makes sense.
But crucially, as you pointed out with the whole I like tea potatoes example,
Yeah.
they are often inconsistent with actual human judgment, which is why human evaluation remains absolutely indispensable.
Because we get context and nuance.
Precisely. Humans are uniquely capable of understanding context, nuance, real-world meaning in a way models often just miss. The trade-off, though, it's expensive.
Right.
And unlike automated metrics, it won't be perfectly repeatable even if you use the same humans in the same context. There's always some subjectivity.
Okay, so if no single metric, no LLM judge, not even human evaluation alone is the silver bullet,
Mm-hmm.
what does this all mean? How do we actually get reliable results in practice?
It means the emerging and I think powerful approach is recognizing that together is better. It's about creating a sophisticated blend.
Okay.
The Databricks R Catbot system provides a really cool illustration of this. Their initial approach using GPT 3.5, it produced inconsistent results, mostly due to that LLM-induced bias and subjectivity we talked about. So they partnered up for a process they called LLM as a judge with human enablement. Basically, they aligned on clear goals, they built a specific scoring rubric, they brought in domain experts.
Ah, the experts.
Yeah, and crucially, they used human-generated golden data sets to actually retrain their LLM judge.
Oh, interesting. So they essentially taught the GPT 3.5 judge how to judge better, using human insights as the gold standard.
Right.
That's quite clever. And the results? Did it work?
It really did. This effectively brought GPT 3.5 performance much closer to GPT-4 levels on their specific task.
Wow.
And this success story just underscores that human-generated data remains a fundamental piece of the puzzle, especially for achieving higher performance while keeping those costs under control.
Right.
Plus, thinking about how you ask questions matters too. Incorporating diverse question types, maybe informed by frameworks like Bloom's taxonomy, can significantly enhance how systematically you evaluate chatbot responses.
So it's about building this robust, multi-layered system, not just relying on one potential point of failure.
Exactly. It's a system, not a single test.
Ultimately, then, LLM evaluation needs to go beyond just the technical performance metrics and connect directly to what truly matters for a business. Yeah.
Absolutely. The bottom line has to be, what's the cost, maybe in dollar terms, if your LLM gives a not safe for work response? Or what if a legal LLM provides bad advice? Businesses need to determine these potential costs to decide how much to invest in metrics, in safeguards, or even how much latency they can tolerate for, say, online safety checks. Metrics, at the end of the day, they should give you magnitude and direction. They're there to help you drive critical business and technical decisions.
So they're tools for making strategic choices, not just academic scores on a leaderboard.
Precisely.
That's a really crucial insight, connecting the technical stuff to the tangible business impact. Okay, so shifting gears slightly. Beyond just evaluating their outputs, making these massive language models actually work efficiently in the real world is another enormous hurdle.
Huge hurdle.
My sources mention that training these things is an operationally expensive endeavor. And I imagine that's not just financially right, but sheer computational requirements too.
You're exactly right. I mean, we're talking about models with billions, sometimes even trillions of parameters.
Trillions.
And here's a truly surprising fact from our sources, one that really stopped me in my tracks. Training a single large language model can emit as much carbon dioxide as 5 cars would in their entire lifetimes.
5 cars over their entire lifetimes.
No.
That's absolutely staggering. It really puts the cost of AI into a whole new, much more urgent perspective, doesn't it? Beyond just the dollar signs.
It really does, a stark reminder.
So what are we doing about it? How are engineers and researchers tackling this immense operational intensity, this energy cost?
Well, that staggering energy cost is precisely why the innovations we're about to discuss are so critical.
Yeah.
It's not just about saving money, it's about real-world impact, sustainability, and frankly, democratizing access to powerful AI. If we connect this to the bigger picture, this operational intensity directly drives innovation in how we build and run these models. For memory and speed, one of the key techniques is quantization.
Quantization. Okay, can you break that down for us? What does that actually mean?
Sure, think of it like this. Normally, a model's internal calculations use very precise numbers, right? Like floating point 32-bit numbers. Think of it like a high-definition photograph.
Okay.
Quantization is like taking that high-definition photo and saving it at a slightly lower resolution or maybe with fewer colors. It involves reducing the precision of the model's weights, those internal parameters, from standard formats like FP32 down to FP16, 8-bit, or even 4-bit.
And the benefit is?
The benefit is it drastically cuts the memory footprint. For example, one source mentioned the octocoder model saw its required GPU VRAM drop from 32 GB down to just over 9 GB with 4-bit quantization.
Wow, that's a huge drop.
It is. And it can also speed up calculations, especially since many modern GPUs actually have hardware support optimized for these lower precision calculations.
So there's a trade-off, I assume? Like you lose some accuracy?
There is a trade-off, yeah. Usually a slight loss in accuracy, but often it's surprisingly small. And the benefit is it makes these powerful LLMs runnable on much more accessible, consumer-grade hardware sometimes.
So the clever way to fit these massive models onto smaller, more affordable hardware.
Yeah.
Effectively democratizing access, like you said.
Precisely. That's a big part of the goal. Another crucial technique, especially for generation, is the key value cache.
Key value cache, okay.
So in autoregressive text generation, that's where models produce text, one token, like one word or part of a word, after another.
Like generating a sentence word by word.
Exactly. A significant bottleneck is recalculating what's called attention over the entire sequence of text generated so far at every single step.
That sounds inefficient.
It is. The key value cache dramatically speeds this up because it stores the results of past computations. So only the current token needs full processing based on the cached history.
Ah, I see.
It's often enabled by default in popular libraries like Hugging Face transformers, and it leads to really significant speedups, especially for longer input sequences.
It's like the model remembering what it just calculated, so it doesn't have to redo all that work every time it adds just one new word. That makes a lot of sense.
You got it.
But speaking of longer sequences, a major fundamental challenge for the original transformer architecture is that its computational cost grows quadratically with the sequence length. It gets exponentially slower as the text gets longer. How are people tackling this long context problem?
That's a really fundamental challenge, yeah, that quadratic complexity.
Right?
To handle truly long contexts, we're seeing major innovations in things like advanced positional embeddings, techniques like rotary position embedding, or rope and alibi.
Ropey and alibi, what do they do?
They essentially give the LLM better cues about the order of words or tokens, especially over long distances. They modify how attention is calculated, the query key computation, to directly incorporate position information.
Cool.
Our sources suggest that while rope might need some effective tricks to extrapolate well to longer sequences than it was trained on, alibi is known to extrapolate much better out of the box. You see alibi used in models like MPT and Bloom.
So they're essentially teaching the model how to keep track of where it is in a really, really long document without getting lost, even if it's much longer than anything it saw during its initial training.
That's a great way to think about it, yeah. And beyond just embeddings, engineers are also redesigning the core attention mechanism itself through efficient attention mechanisms.
Okay.
To reduce a memory bandwidth bottleneck during that autoregressive decoding, one technique called multi-query attention, MQA, reduces the number of internal key value heads the model needs to project.
Fewer heads, less work.
Kind of, yeah. And an improvement on that is grouped query attention, or GQA. It takes this further by using just a small number of these projection weights, maybe 2, 4, or 8, shared across groups of queries, instead of just one per query like MQA or one per head like the original multi-head attention.
And that helps.
It helps a lot. And what's really cool is that GQA can apparently be uptrained into existing model checkpoints with as little as 5% of the original pre-training compute.
Wow, only 5%. That's efficient.
Very efficient. It makes it highly valuable for things like chat applications, and you see it used in models like Llama V2.
So it's making the model more focused and efficient at understanding context, especially in real-time conversations where speed matters.
That's a good way to put it. And then, taking it even further, we have a newer architecture called Sliding Window Attention Training, or SWAT.
SWAT.
This is designed specifically for efficient long-context LLMs. It actually replaces a traditional internal function, the softmax activation, with sigmoid. The idea is this helps with better information compression and retention over long sequences.
Interesting change.
Yeah, and it also uses a clever combination of balanced alibi and rotary position embedding to stabilize the training process. Specifically, it addresses something called the attention sink phenomenon.
The attention sink phenomenon, that sounds intriguing. What exactly is that?
It's this tendency some models have, especially with long inputs, to allocate excessive attention, like way too much focus, on the very first few tokens of the input.
Ah, like getting stuck on the beginning.
Sort of, yeah. Almost forgetting to pay enough attention to the rest of the text. SWAT helps the model avoid this kind of mental block.
I see.
And the result is it maintains consistent performance across varying sequence lengths, it excels in tasks needing that long-range understanding, and it achieves linear computational complexity during inference.
Linear complexity meaning it scales much better with longer inputs, unlike the original quadratic problem.
Exactly. Big improvement for long documents.
That's fantastic. Okay, so beyond just making models faster and less memory intensive through these, clever architectural tweaks, the very way models learn is also being revolutionized. We're talking advanced training strategies now.
Absolutely. And this raises a really important question. How do we make models learn more effectively from the data they do have? And maybe even how do we make them unlearn information they shouldn't retain?
Right, the unlearning aspect is crucial.
One powerful answer here lies in contrastive learning.
Okay, contrastive learning. What's the core idea behind that?
At its heart, contrastive learning is about teaching a neural network to learn meaningful representations, like internal concepts, autonomously, often without explicit labels for everything.
Learning by itself.
In a way, yes. It does this by processing pairs of data. You have positive samples, which show similar content. The model learns to pull these closer together in its internal latent space. You can think of that like a conceptual map inside the model.
Okay.
And then you have negative samples, which show dissimilar content. The model learns to push these farther apart on that map.
So it's learning by comparison. This is like that, but this is different from that.
Exactly. That's a great way to put it. This process leads to models that often generalize better and are more resilient.
Makes sense.
Yeah.
And how does this apply to that unlearning problem?
Well, a direct and really critical application is machine unlearning. With regulations like GDPR, the right to be forgotten is a big deal.
It's huge.
But retraining these massive LLMs from scratch every time you need to remove one person's data, it's just computationally infeasible. It would cost a fortune and take forever.
Right.
So DeepCUT, which is a contrastive unlearning framework, addresses this. It works by directly optimizing the model's latent space, that internal map.
Now,
It basically pushes a forgotten sample, the one you want to remove, called the anchor, away from other samples in its original class, while simultaneously pulling it closer to samples in different classes.
oh, okay. So it confuses the model about that specific piece of data.
Effectively, yes. It removes the memory of its unique features without degrading the overall performance of the model on other tasks.
That's incredibly powerful. Being able to selectively forget specific data without needing to wipe the model's entire memory and retrain it from zero.
It's a potential game changer for privacy and compliance, absolutely. Yeah. Another application of contrastive learning ideas is in PII detection, personally identifiable information, say, in network traffic. This often uses a specific type of loss function derived from contrastive principles called triplet loss.
Triplet loss. Okay, that sounds like it involves sets of three, like you said.
It does. Triplet loss is a really clever way for the model to learn by comparing three things at once: an anchor item, a positive item, something similar to the anchor, and a negative item, something dissimilar.
Anchor, positive, negative. Got it.
The goal, the objective function, is to train the model so that the anchor's internal representation is closer to the positive's representation than it is to the negative's representation, usually by a certain predefined margin.
Pushing the negative further away than the positive.
Exactly. And to make this training efficient, because you could potentially create billions of triplets, they use techniques called triplet mining.
Mining.
Yeah, it's basically smart ways to select only the most informative or challenging triplets for the model to learn from during training. Things like batch hard mining or semi-hard mining. It helps the model focus on the comparisons that will teach it the most.
I see.
And this triplet loss approach. It's particularly useful for tasks like few-shot, highly multi-class text classification, meaning situations where you have a large number of different categories, but maybe only a very small number of training examples for each one. Triplet loss helps the model learn good distinctions even with limited data per class.
Fascinating. It's like a smart tutor that knows precisely which examples will teach the model the most useful distinctions. What other training innovations are shaping how these models learn?
Well, another really interesting one is curriculum learning, and specifically a variant called curriculum data augmentation.
Curriculum learning, like a school curriculum.
Exactly like that. This training strategy mimics how humans often learn. You start with easier concepts and gradually increase the difficulty.
Makes sense.
So instead of just throwing all your data, including maybe augmented or potentially noisy data, at the model all at once,
Right.
curriculum data augmentation first trains the model on the original clean examples. Then, only as training progresses does it start introducing the augmented or noisier data. Easing it in.
Precisely. This might involve a simple two-stage process, or maybe a more gradual schedule, where the amount of noise or augmentation, sometimes controlled by an augmentation temperature, linearly increases over the training time.
And the benefit of this gradual approach.
The research suggests it can lead to faster training, often improved final performance, and better robustness, meaning the model can handle noisy inputs better, even when trained with quite high amounts of data noising eventually.
So it's about smart data exposure, not just more data, letting the model build a solid foundation before tackling the harder or maybe messier information. That makes a lot of intuitive sense.
It really does.
And all these advanced training techniques, they ultimately rely on the fundamental optimization principles that govern how these models learn in the first place, right? The real nuts and bolts.
Exactly. You can't forget the basics. At the very, very core of training, almost all these deep learning models is the gradient descent algorithm, or one of its many variants.
Gradient descent,
Yeah.
the classic. The classic. It's the workhorse. It iteratively adjusts the model's internal parameters, that huge weight matrix, in a direction that minimizes the loss function, which is just a measure of the model's error, how far off its predictions are from the actual truth.
Trying to get less wrong over time.
That's the goal. And for handling the truly enormous data sets we use for LLMs, you pretty much always use stochastic gradient descent, SGD, or an adaptive version like Adam.
Stochastic, meaning random.
Well, probabilistic, really. Instead of calculating the error gradient over the entire massive dataset at each step, which would be incredibly slow, SGD approximates the gradient using just a small random sample, a mini batch of examples, typically maybe 32, 64, or 128 examples at a time.
Oh, okay.
The size of these mini batches is actually a critical hyperparameter you need to tune. Often the advice is to make it as large as you can until you run out of GPU memory.
Pushing the hardware limits.
Pretty much. But this probabilistic approach, using small batches to approximate the true loss function gradient, that's precisely where this stochastic part in stochastic gradient descent comes from. It's what makes training on these truly enormous data sets computationally feasible.
It's amazing how these fundamental ideas underpin all the complex stuff we've been talking about. So we've really journeyed through this intricate landscape today. We started with LLM evaluation, looking at the challenges of single metrics, the pitfalls of LLM judges, but also the power of combining automated checks with human-in-the-loop systems. Then we dove into the remarkable innovations making these models more efficient. Things like quantization, key value caches, new attention mechanisms making them less memory hungry and able to handle vast amounts of information, like with rope, alibi, and SWOT.
Yeah, it's clear that building and evaluating truly robust LLM applications requires this multifaceted approach, doesn't it? It's
Yeah.
definitely not just about chasing a single score or using one simple algorithm. It's really a sophisticated blend of different metrics, that critical human insight we keep coming back to, and these advanced optimization and training techniques, all working together to really understand the model's behavior and unlock its full potential.
And we've seen how this continuous innovation, both in how we train and how we evaluate these powerful systems, is just crucial for pushing the boundaries of AI, making it more accessible, more effective, and hopefully more responsible too.
Well said.
Which brings us to our final provocative thought for you, the listener. As we get better and better at making LLMs selectively unlearn specific data using techniques like contrastive unlearning, or as we optimize their internal representations more finely, what new, perhaps subtle biases might we inadvertently be creating or uncovering? And what will be the next frontier for how we even begin to measure those unforeseen consequences?